Okay, cool. Thank you very much for coming. Today we have Nikola Sandric. He will be talking about convex hulls of random walks.
Thank you, and hi everyone. Also, I would like to thank the organizers for the opportunity to present one of my works here on this program. So this is a joint work with Wojtek Cigan and Stjepan Šebek, and I'm going to talk about convex hull of random walks. Okay, let us first start with the description of the problem. So our main object will be a d-dimensional random walk, which we denote by Sn. The walk starts from the origin, and by yi we denote the corresponding jumps. So this is a sequence of IID vectors in Rd. And actually, we won't be interested in the walk itself, but rather we'll be interested in its convex hull. So we let the walk run up to time n. So in this way, we get at most n+1 points in our state space in Rd, and we take a convex hull of these points. So this is a compact and convex set. Actually, it's a polytope, right? And our aim is to study evolution of this polytope, this convex set. And not only the set, but also we'll be interested in certain functionals of this set. So in the two-dimensional case, the most natural functionals are perimeter, diameter, area, etc. And we'll try to find also and define analogs functionals in higher dimensions. Okay, so now at least intuition tells us that we should expect a different behavior depending on whether our walk has zero or non-zero drift. Because in the zero drift case, we expect some kind of symmetry. We expect that this convex hull involves around the center of the state space, while in the non-zero drift case, we expect that involves in the direction of drift. And I have two small animations which actually support this intuition. So the first one is in the zero drift case. So we see how this red thing is a convex hull of the points. So it involves around of the center of the state space. And on the second animation, we have a random walk with drift, and drift is 1, 1. Okay, okay, and somehow it goes in the direction of the drift. Okay, so also we expect this thing to somehow be visible in limit theorems, and we'll see that actually this happens. Okay, so let me now say a few things about known results. So this type of problems people started to study roughly 60 years ago. Of course, first in the dimension 2. So again, we use the same notation, and also by Ln I will denote the perimeter of our convex hull, and by An we'll denote the area, and later we also have diameter. Okay. Okay, so first result in this direction is due to Spitzer and Widom from 1961, and they derived a very nice formula for the expected value of the perimeter, which is given in terms of the walk itself. So this formula can be very useful when one wants to study limit theorems of this object here. A similar formula for the area was derived by Barndorf-Nielsen and Baxter 2 years later, and is given by this relation here. So this functional here, T, of two vectors, x and y, so these are two-dimensional vectors, is nothing else than the area of the triangle with sides x, y, and x plus y. Okay, so expected area is given in this with this formula here. Okay, so now we would like to get something similar for some multi-dimensional analogs of these functionals. So perimeter, area, and maybe we'll see that there are also some others. First, let us define these functionals. Okay, our polytopes, convex hulls, live on this space, state space. So this is a set of all convex bodies. These are convex and compact sets. If we handle this set with the Hausdorff distance, so just to recall what is a Hausdorff distance, then this pair becomes a complete metric space. And this will be important for us. We will study limit theorems, in particular weak limits. So we can conclude some things from this, of course. Okay, Next, let us take a set A from K and take a non-negative, strictly positive real number. Then we will define outer parallel body of A at distance rho as this set here. So BD is nothing else than the closed unit ball centered at the origin. So what we did here, nothing else that we just take closed rho neighborhood around A. Okay, and then we are interested in the volume of this set here. So the volume here is nothing else than the d-dimensional Lebesgue measure. And then the famous Steiner formula tells us that this volume can be written in this form, this polynomial form. So the polynomial in rho with these coefficients here. So this kappa here, so kappa k, is nothing else than the volume of k-dimensional ball, unit ball. Okay, so it's this constant here. And what is very important and interesting for us are these constants here, which depend only on the set A. And these are called intrinsic volumes. So this object here gives us information about the content of set A. What I mean by that, okay, let me say what they are. The last one, VD, is nothing else than the volume. So it's the d-dimensional Lebesgue measure of A. This one, VD minus 1 times 2, is the surface area of this set. The first one, okay, V0 is just constant. Okay, this is just notation. The first one, V1, is mean width, or it's proportional to mean width, and mean width is defined in this way here. Okay, through this function SA, which we call support function of A. Maybe a small picture. What does this function do? So observe that the parameter of this function is we take on a boundary of unit ball. Okay. So this function what does? Of course, I'll draw it in the two-dimensional case. Let's say that our convex polytope is just a rectangle. We take our angle theta and we project this object on this line. Okay, when we project it and we take maximum value. So the maximum value will be the maximum, when we project this rectangle on the line, the maximum value will be exactly this thing here. Of course, the projection is everything between these 2 points, right? But we take the maximum. Okay, and we do this for all angles, or we do this for all points on the boundary of the unit ball, and we integrate everything with respect to the surface measure, so uniform measure on the boundary. Okay, and in this case we get the mean width. So if we take for A to be just the unit ball, here we'll get, can you guess? 2. Okay, just diameter, 2 times radius. Okay, so this is mean width and it's proportional to V1. Okay, and in the two-dimensional case, V1 and these 2 are the same, up to a constant. Okay. What about the others? Vk. So we have so far we just explained what are Vd, Vd minus 1, and V1. Well, for the others, actually, there is no such a nice interpretation. Maybe the best way to explain them is through this formula, which is called Kubota's formula. So Vk of A can be understood or intuitively explained in this way. So it's some constant which depends on the dimension of the state space and this parameter k, something. Then take our set A, take a rotation in the d-dimensional space, in our space. So Q will be some orthogonal matrix, and take a projection, which we call, let's say, pk, on any fixed k-dimensional subspace. Okay, so if you're in 3 dimensions, we are interested in V2, we can take any plane, x, y, y, z, or any other plane, doesn't matter. And then take volume of this object, because now this is a k-dimensional set. We made a projection. Okay, and then average everything with respect to all orthogonal matrices or rotations, but not any SO special orthogonal group, so determinant is 1. With respect to hard measure, uniform measure on this space. Okay, so in this sense, this gives us information about the K content of our set. Okay, at least I hope that you get some intuition what VK means.
Which projection you take?
Any. You fix the plane on which, because anyway you will make rotations, all rotations. So it doesn't matter which plane you choose or subspace.
Yes, okay.
Okay, so because anyway you go over all rotations. So if you choose some other, then some other rotation will give you the same. And the measure is of course uniform. So the weights are the same. Okay, so now we'll use this notation here. And as a first step, we will be interested in formulas like this, but for intrinsic volumes. And these things are known. These things were obtained quite recently in 2018 by Vysotsky and Zaporozhets. So they showed that expected intrinsic volume can be computed in this way, or represented in this way, where these objects here are just independent copies of our original work. Okay? So if you put here K1, you will get exactly this thing here. So this Spitzer-Widom formula extends to any dimension, because in the two-dimensional case, we had here perimeter, but perimeter is 2 times V1. Okay. Also, they obtained a concluded formula like this for the last one, for the volume, expected volume. Okay, so just determinant of this matrix here, and this matrix, so the columns of this matrix are these walks. So if you recall the meaning of determinant or absolute value determinant, it gives you just a volume, which is volume of the object which is spanned by these column vectors, right? And you additionally average everything. Okay. And if you put d equal to 2 in the two-dimensional case, so we have in two-dimensional case, we're interested in area, we get Bandor-Nielsen-Baxter formula, the one given with this operator t. Okay, exactly the same. Okay, so we do have analogous formulas for intrinsic volumes. Okay, so now we are interested in limit theorem. Okay.
Question. So
Yeah.
all of these formulas look kind of linear. I guess there must be a really good reason why it's so nice.
The proofs are combinatorial, purely combinatorial. Yeah.
You got exact formulas.
Yeah, exactly. So exact formulas. Yeah, it's very nice. Yeah, and the walk can be anything. Doesn't depend on moments or anything. Okay, now limit theorems. First, zero drift case. We expect two types of behavior. And we assume that we have finite second moment. Later, I will relax this assumption. Okay, and by sigma, I'll denote this covariance matrix. Okay, by BTD will be a standard d-dimensional Brownian motion. And by this symbol here, I'll denote its path, but as a set, up to time n, from 0 to 1. Okay, now Donsker and continuous mapping theorem gives us this result here. Okay, just a small short explanation how and why. Observe that this set is exactly the same as this one. Okay, and we scale this by square root of n. By Donsker, we get the Brownian motion in the limit. This is first thing. Second thing, what is known, that if you take Cadillac path, so from interval 0, 1 to RD, and we construct the following mapping which takes its trajectory, and then we take closure, topological closure, and we take a convex set of this object, then this mapping is continuous. This can be shown between Skorohod space and our space K with Hausdorff metric. This is continuous. So if we combine these two things, we use just Skorohod and continuous mapping, and we conclude this convergence, V convergence. Okay, it's very easy. Now we can switch to intrinsic volumes. So for intrinsic volumes, it's known that they are also continuous, and plus they are homogeneous with order k. So Vk is homogeneous with order k. So when we apply Vk on this convergence, we get this one. Okay, it's very nice. So now it would be interesting to say something about this thing here. So kth intrinsic volume of the path of Brownian motion up to time 1. Okay, this is something like this. Okay, people also studied these things. So again, first results are from the two-dimensional case, from the planar case. And let us denote by L1 the corresponding perimeter, and by A1 the corresponding area. Okay, 1 because we consider a Brownian motion up to time 1. Okay. Then results by Letak and Takash from 78 and 80, they independently prove that the expected perimeter is square root of 8 pi. It's very interesting. Then later, El-Bahir in 1983 showed that the expected area is pi over 2. Okay. Here also one may consider the diameter of this object. For the diameter, the things are a bit more tricky. So we don't know the exact value, but we only know bounds. So first observe the following inequalities, which are quite trivial, I guess. So this inequality says that the perimeter is between d times pi and 2 times d. And I think that it's, at least intuitively, should be clear how to conclude this, because this inequality says that among all convex shapes with diameter d, one with largest perimeter is the disk, right? And that one has perimeter p times d. And the smallest one is the line segment, because perimeter is go one direction and go back. It's 2 times diameter, right? Okay, so from this relation and this fact here, we easily conclude upper and lower bound of this object. These bounds were further improved by McRedmond and Shu in 2017. So they got this weird constants. And later by Jovalekic and also unpublished work by Rachel and Garbit, they improved lower bound to 1.86. So if somebody wants to play, there is still enough room to improve these bounds. Yeah. Okay, as I said earlier, so we are interested in some distributional properties of this thing here, in particular expected value of this thing here. And for this, in the Brownian motion context, this is known for all intrinsic volumes. This is a result by was proved by Eldan in 2014. Then Kabluchko and Zaporozhets showed the same thing in 2016. Different methods, and Molchanov and Vespy showed in the same year, but they proved it in a slightly more general context, in the context of stable processes. So when index of stability is 2, when we are in the Brownian motion case, then everything reduces to this here. So we have very nice closed form. Okay, so now let us move to the non-zero drift case. Still, we assume that we have finite second moment. Okay, again, small picture, but this time we have a random walk. Again, the drift is just 1, 1, but we now have 2,000 steps. Okay, so now from this picture, we can guess, the picture suggests that in this non-zero drift case, if we look at perimeter, the perimeter should scale with n, right, with the number of steps. And we expect that the limit is 2 times the drift, if it scales with n, right? So we go in one direction and we go back. And for the diameter, we expect that it also scales with n. At least this is what this picture suggests, and that converges to the length of the drift, right? Okay, the diameter should be this. And for the area is a bit more tricky, so to guess the scaling and what we get in the limit. We'll see it later. And in these, this is true. So the strong law, large numbers, in this form was proved by Snyder and Steele in '93, but under the assumption that an assumption of finite second moment. This was later improved by McRenmond and Wade, 2018. They showed the same thing, but under assumption just of finite first moment. And they also proved the strong law large numbers for the diameter. Okay, so this is exactly the results we expected from the picture. Okay, now when one has strong law large numbers, one can ask also whether can one get something in the central limit theorem direction. And this is actually true. But the important thing here is to consider this number here. So by mu hat, we denote the unit vector in the direction of the drift. And this is nothing else than the variance in the direction of the drift. Okay, so it gives us information about randomness in the drift direction. And if this, so for example, walk with these steps will not satisfy this. So this is just constant 1. And this is Bernoulli with jumps -1 + 1. Okay, random walk with this jumps won't satisfy that condition, for example.
Sure, can you explain this again? This last part.
Yeah, well, if you draw a picture, that walk moves 1 and jumps up and down. Okay, so it and if you project everything on the direction of the drift, which is x-axis, it's deterministic. Okay, so it doesn't have to be symmetric. So you just need ±1. Okay, and if this variance is not 0, Wade and Shrew proved central limit theorem for this thing here. It's a classical central with normal limit and with classical scaling. And the same thing they proved for the diameter. If this object is 0, then one can show that this thing here, of course, without this constant, because this is 0, that this thing here converges in L2 to 0. And this one as well. Moreover, one can prove that this thing here, without any scaling, converges in distribution to chi squared times some constant. And I think the same holds for the perimeter. Okay, so one really gets also in this, when this is 0, this case limit theorems, what with non-normal limit. Okay, so but what to do with the intrinsic volumes? Okay, so basically, what is our idea now is not to consider the path of our random walk as a d-dimensional object, but rather as a time-space object. So we'll consider the drift direction as a time and everything which is orthogonal to the drift as a space. So we'll consider this as a time-space object of d-1 dimensional random walk. So we have this will be time, and these movements will be orthogonal to the drift. So to do that, we will make a rotation of our walk. Okay, so E will be our standard orthonormal basis. Now we will make a rotation of our basis. So we will define E bar basis in a way that E1 is just the direction of the drift, and the rest, of course, is just orthonormal basis. Okay, and then we will make a rotation of our walk. So we will make rotation of the jumps in this way. Okay, we just transfer it to the new orthonormal basis. And in this way, our walk in the first coordinate will be just direction of the drift, and all the rest will be orthogonal to the drift. Okay, and all the rest we have expectation 0. So we will have d-1 dimensional random walk with expectation 0. So we are going back in the previous situation, and plus we also have this drift moving. Okay. And also I'll denote by sigma mu orthogonal this covariance matrix. Okay, so this y bar orthogonal is this vector here, d-1 dimensional. So we just move away this drift direction here. Again, also I'll define by mu tilde mu orthogonal this matrix. So this is this mu sigma mu orthogonal from before, and we also add one row and one row, a column in this way. Also, we define psi, the following transformation, linear mapping in this way. So we have rotation and we have scaling. So observe now, this is strong low large number scaling. This is in the direction of the drift. And the rest is CLT scaling. Okay, so it's this Brownian scaling because we have finite second moment. Okay, and further, we don't expect any more Brownian motion in the limit, but we expect time-space trajectory of a d-1 dimensional Brownian motion, because this is exactly what it did with this transformation. Okay, so the first will be drift and the drift direction, and this d-1 objects will be just random walk, zero drift random walk, finite second moment. Okay, and again, using same ideas as before, Donsker and continuous mapping theorem, we conclude that under this transformation, our convex hull converges to convex hull of this time-space trajectory of d-1 dimensional Brownian motion. Since intrinsic volumes are continuous, we also have this result. And in the last intrinsic volume, so in the volume case, we also have this bit nicer form, which can be easily concluded from the fact that this mapping here, so this is linear, and it can be written as a composition of an orthogonal mapping, so the one which rotates our coordinate system, and this scaling mapping. And what is this scaling mapping? This is just nothing else than the diagonal matrix. Okay, so in the first position we have 1 over n time mu, or norm mu, second position 1 over square root of n, and so on. And the determinant of this diagonal, well, first of all, volumes are invariant under rotations, orthogonal transformations. So we don't care about this orthogonal matrix. What is only here important is this object here, and we know how volume reacts on such transformations. We just take determinant, and this is exactly what we get here. Okay, and times mu, but we put mu here, and the same is here. This is just we have determinant. Determinant of this object here is exactly this. Okay, so we. Okay, now also one may ask what happens with the convergence in mean. Okay, so okay, this is this matrix Dn. Okay, if we have additional assumption on the moment, like this one, then one can conclude that this sequence is uniformly integrable, and this plus previous theorem, previous results, gives us convergence in means. Okay, get something like this. And in particular, we also conclude this. So this last line follows from this last. Okay, okay, now also an interesting question is whether one can conclude a similar convergence to this one for other intrinsic volumes. But because here we have this, well, not very strange, but in a sense, strange transformation. We have multiply everything by this matrix. So we'd like to have this something of this form. So expected value of intrinsic Kate in intrinsic volume divided by some scaling, some constant, okay, or some sequence. Okay, and this actually can be done. This can be done. So the result is as follows. Okay, so given this form, okay, it's not really practical. This integral form. So if one has finite moments of this order, then the appropriate scaling is this one. It's similar to this one, of course, and the limit one gets is this here. Okay, so what we do here? So actually, we take this this formula here. So what we do, similarly as before, we need to make a transformation of our coordinate system. So we again at the beginning we fix we are interested in the intrinsic volume of Kate intrinsic volume. So we fix arbitrary k-dimensional subspace. so through this projection pk, and we take one rotation, one orthogonal matrix. And for this Q, we define orthonormal basis EQ in a way that this first one, the first coordinate, is exactly in the direction of this transformed drift. So we rotate the drift vector and we project it on a k-dimensional subspace, and we, of course, we need it to be of length 1. And the rest is just orthogonal. Then we take this transformation here, it just gives us the part which is orthogonal to the drift. Okay, because we are again doing this space, time-space transformation of our process. So this time-space process is given in this form. So first we have this time, and now we have space. We take our Brownian motion from the limit, which we rotate, which we project it, and they take just the part which is orthogonal. Okay, and then we average everything with respect to all rotations. Okay, so it's a bit messy. It's, as I said, it's not practical, but this is something that one gets in the limit. Just to compare this one and this one. These two things are not the same object in general. Okay. When k is 1, then we get something stronger and a bit nicer. We get something like this. Okay, and these two things coincide. So when k is 1, we actually have here, and so exactly for k1, this thing here is exactly length of the drift vector. Okay, now it would be interesting to say something about this thing here. So expected value of this of the volume of the time-space Brownian motion. Okay, because in the Brownian motion case we know I showed you this formula here, and we also managed to do something in this case. Okay, but only for the, not for any intrinsic volume, but just for the last one, just for the volume. We managed to compute it, and the formula is this one. Okay, how one does this? Well, it's not very hard. The idea is quite simple. So first step is to find one appropriate random walk for which we can compute this explicitly, and such that this thing here converges to this. Okay, and this is quite easy. So we just take S to be a random walk with these jumps. So first coordinate just deterministic 1 because it's time-space object, and this is the -1 dimensional normal. Okay, standard. Okay. And then, using the result by Vysotsky and Zaporozhets, this the expected value of the volume of this walk can be written in this form here. And it is known that with this scaling converges to this thing. Oh, sorry, to this one. And now we just left to compute this thing here. And this can be computed explicitly, just one little place with these things, because these are very nice variables normal. And one gets this thing here. Yeah. Okay, so far I discussed only the case when we have finite second moment, or maybe higher moments. Now let me say a few words, not much, about the case when we have only, the moment, second moment doesn't have to be finite. So then we are, well, naturally in the domain of attraction of stable laws. So we assume that our jumps belong to the domain of attraction of some stable law. That means that there are sequences Bn and alpha n such that this thing here, such convergence in distribution holds. And this is, of course, this means that actually behind we have some alpha stable Levy process, which we denote by xt. Also, what is known that we know actually how this centering and normalizing constants look like. So when alpha is strictly smaller than 1, this constant can be taken to be 0. When alpha is 1, then it's something of this form. And when alpha is larger than 1, this is just the drift of our random walk, of course. And normalizing constants are of this form. So n to the power 1 over alpha. Recall that in the Brownian case, it's 1 over 2. Well, Brownian case is also covered by stable, of course. And Ln is a slowly varying function at infinity. Essentially, this is kind of logarithm or something. Okay, and in this case also we have kind of this version of Donsker theorem, okay, CLT theorem on the this space of Cadillac functions. Okay, Now, again, similarly as before, continuous mapping theorem gives us this convergence here in this context. And also we can, due to fact that intrinsic volumes are continuous, and also, again, they are homogeneous of order k, we also conclude this relation here. However, we are interested in on the convex hull of this object here, not of this here. So essentially, these results are only informative when an is 0. Okay, so let us first consider this case when an is 0. In the case when alpha is strictly bigger than 1, which means that we have finite first moment, and this essentially means that the drift is 0. Okay, again, we are in a similar situation as before. In this case, we have following results. Okay, so CLT we have here, or CLT, sorry, convergence in distribution. Now convergence in means are given here. Okay, we don't need any assumptions. So this is for all intrinsic volumes. Okay, holds for this, and then we can also conclude that holds this convergence. So we first prove this thing here, and then we show that this object here is equal to this one. So that's the idea. So these things are the same. And these processes X, M, L, and so on are independent copies of our process X. So this is a stable process we get in the limit. Okay, so now again, it would be interesting to say something about this thing here, just to compute it explicitly as in the Brownian motion case. And this also, in certain cases, can be done. So if you are interested in V1, then this thing here just reduces to this. So in some cases, when this stable random variable is nice enough, then we can compute this explicitly. For example, when X is a Brownian motion, then this is just chi squared with d degrees of freedom. In the general case, well, not very general, but in the case when X is symmetric alpha stable, not necessarily rotationally invariant, but just symmetric at this moment, then Molchanov and Vespi showed that there is a unique compact and convex set K such that this expected value is given in this form here. Okay, so it's just this universal constant times the intrinsic volume of this set K. And if we are in the rotationally invariant situation, so we have more regularity, then we expect that this K is more regular, and this is actually true. So it's a ball of certain radius. So if our X is stable with this characteristic exponent, then this set K is just given in this form. So for example, if X is a standard Brownian motion, then gamma is 1/2 and alpha is 2. So just plug this in and we can easily compute it. Okay, again, the case when drift is not 0, again, it's the harder thing, and we can do less things more explicitly. So first of all, also in this case, we have strong law large numbers. Okay, so for V1, okay, so V1 scales with n, and it converges almost surely to the length of the drift. The same thing can be also concluded for the other intrinsic volumes. Okay, here we use just this homogeneity of intrinsic volumes, but the right-hand side for k 2 or more is 0. So this is actually not very informative. Okay, so the scaling is too strong. Again, the idea is to make these rotations and play the same game as before. So let us do it. So take E bar to be orthonormal basis such that the first vector is in the direction of the drift. The rest is, of course, orthogonal. Again, we define these two linear mappings as before. So this one is just rotation, and the second one is just to take the second d-1 components, so the part which is orthogonal to the drift. And take our process, stable Levy process X, and make a rotation. And this is again stable process, okay, with same index stability. and then just erase its first coordinate.
No drift, though.
No, this is just, yeah.
Even earlier, their rotation was to handle the drift.
No, I'm rotating everything, of course.
Handle the drift.
Yes, the drift, yeah, gives the direction of the rotation, yeah. And then here I'm deleting the first coordinate, and this is again alpha stable, but now d-1 dimensional. Okay. And of course, as in the Brownian case, I don't expect Brownian limit, but something time space object, and this will be our x tilde, which is here we have time, and the space is this object here. So d-1 dimensional stable process, and this is a Levy. It's not stable anymore, but it's a Levy process. Okay, and we also define this mapping transformation. So is as before, is just first I do rotation and then I do this scaling here. So again, first component I scale, I have strong low large number scaling. So this is the drift direction, and the rest is this weak convergence scaling. So these are this Bn, recall it's n to the power 1 over alpha times this slowly varying function. Okay. Okay, and then I get this thing here in the limit. Okay, and okay, so since intrinsic volumes are continuous, I can also conclude similar things for this object here, and in particular for the last intrinsic volume, for the volume, the true volume, I conclude this one because of this very nice shape and of the volume itself and this transformation matrix Dn. Okay, unfortunately, in this case, here, okay, we haven't managed to prove anything about the expected, or better to say here, about the expected volume of this convex hull. For the time-space Brownian motion, we managed to do it, but for stable process not, because we need higher moments. If we have higher moments, then we are again in the Brownian world, right? Okay, so we didn't have anything. Here we at most have one just finite first moment, but it was not enough because at some point we needed uniform integrability. So this is open thing. Okay, now one may ask, can one say something about the convergence of higher moments, in particular variance? Yeah, one can conclude it in a similar way as before. So if you are in the zero drift case and our jumps have finite moments of this order, then we can conclude a convergence of variance, which is given in this form here. If the drift is not zero, and again, we have the same order of jumps or moments of jumps, then we have this kind of convergence of the variance, again, to this object similar as before, which is given through this Kubota's formula. And this transform and the definition of this object is the same as before. And when we are interested in the true volume, then we get this thing here reduces to just to this thing here. So observe that here we have a scale with, if you're interested in the last volume, so this one is with d, and this is what d plus 1 or k plus 1 k. Okay, so we need with one order more. The interesting thing to observe here is that if we interested in the first intrinsic volume, V1, so we scale by n squared, but this goes to 0. And this can also be observed from the strong low large numbers. Okay, so it's a too strong scaling. Actually, one can show that for V1, the variance behaves like big O of n. It's not hard to show. And actually, in general, one cannot do better. Why? Well, let me go back almost at the beginning just to comment on this. Okay. So, so these are these CLTs for the perimeter and diameter of in the two-dimensional case. So the results showed by Wade and Shu and McRedmond and Wade. So in this situation, they needed this variance, which is variance in the direction of the drift, and it was necessary that it's strictly positive. Okay, so if it's strictly okay, how one gets this number here? Well, this is exactly the limit of or in this case, ln. Okay, but this is the same up to scaling over n. Okay, so this object converges when you scale with n. So this is really of order n at most. Okay, but when this variance is 0, then of course this is too strong scaling. Okay, and guess is that it's something like logarithmic or something, but it's open. So if one wants to play, it's also one of open questions here. Okay, and of course, at the end, thank you for your attention. Yeah.
Questions for the speaker? So I have a question actually. So in the beginning, when you had the non-zero drift and you had this nice rotation to project everything on the drift space and see it as time. Yeah, I think that was the picture.
This one? Or
Yeah, that's probably the one in the previous one.
yeah, okay.
So
This is
how do you accommodate of the fact that you might have jumps that go on the opposite side of the drift? So so if you see it as space-time, it will be, instead of sometimes going forward in time, it would be like going backwards in time some points, right? If your jump does not go in the direction of the drift and it goes in the other direction.
yeah, but you project it in this way. This is just a form of the linear transformation you do. So
yeah, but that's fixed in the beginning.
yeah, of course, it's fixed.
So let's say that one of the random jumps doesn't go in this direction, but it goes
Yeah, but
in
you-
the opposite.
Okay, but if you have something that goes in this direction and you just project it here, it's a bit something smaller, but you still somehow
As in, it won't.
You don't lose the
it
information.
won't happen that much, that often, so that.
no, you don't lose the information. You just made a rotation in this direction here. Yeah, so you don't lose information. You just squeeze the vector or just prolong it. So yeah.
Okay, I think we can actually, we should take a break probably before the.
Okay.
Let's take the secret.
That's it.